Hello everyone. So let's solve the question based upon the specific energy theory, and these questions are I've picked are mainly from the hump and the width contraction, which I found are something valuable to solve. So first question is, in a rectangular channel 3.5 meter wide and it is having a slope in a depth of 2 meter. How we have to find how high can the hump be raised without causing a flux. So this is the case of a hump, and let's say the flow is occurring like this, and so we have to find out the maximum height of hump such that there is no change in the upstream depth. And then the next part is, if the upstream depth is to be raised to 2.4 meter. So current first of all this depth is 2 meter, and in the next part we have to raise this depth to 2.4 meter, and for that we have to find out the height of hump. And as we saw earlier, the upstream depth can only be raised if this z is greater than the z max. So for that we will see. So first of all, as channel slope and Manning's coefficient are given, we have to find out the velocity and discharge. So we, from the Manning's formula, it is equal to 1 by n r to the power 2 by 3 s to the power 1 by 2, where r is the hydraulic radius and s is the bed slope. So r is equal to a by p. Area of the channel is 3.5 into 2. Perimeter is 2 into 2 plus 3.5. So this is 7 divided by 7.5, and it will come out to be 0.933 meter. So from here, if we put this value in the equation, n is given as 0.015 r 0.933 to the power 2 by 3, and s is 0.0036 or 1 by 2. So the velocity comes out to be 3.819 meter per second. And from your discharge we can find out as A into V. So A is equal to 7 into 3.819, so it comes out as 26.7 6.735 meter cube per second. So from here, first of all we can find out the specific energy upstream. E1 is equal to y1 plus v square upon 2g. Y1 it is given as 2 meter, and v, as we found out, 3.819 square upon 2 into 9.81. So this comes out as 2.743 meters. And for the maximum height of pump, we know that this maximum height will occur when here this height is critical. It is at critical depth. So for critical depth, we know yc is equal to q square upon g to the power 1 by 3, and small q is remaining the same because the width of channel is same at both the sections. So from here yc we can find out as 26.735 divided by channel width is 3.5 meter square divided by 9.81 to the power 1 by 3. So yc is coming out to be 1.812, and from the energy equation, and we know the specific energy corresponding to critical depth is 3 by 2 yc. So 3 by 2 into 1.812, which is equal to 2.718 meter. And if we apply the energy equation between section 1 and 2, so E1 is equal to E2 plus delta Z max. And if this is delta Z max, so this will be EC. E1 as we found out as 2.743 is equal to E2 is 2.718 plus delta Z max. So delta Z max is equal to 0.025 meter. And this was the first part of the question, where it was asked how high can the hum be raised without causing a flux. So a flux means the change in depth here. So delta Z max without any change in depth is coming out to be 0.025 meter. Now in the second part it is saying the upstream depth is to be raised to 2.4 meter. So if we want to increase the upstream depth, it means that delta Z max, the delta Z, it should be greater than the delta Z max. So in this condition, what happens is the downstream will still be at the critical depth, but the upstream depth will change. So the new equation we can write it as E1 dash, which is the specific energy at section 1, is equal to EC, and which is the specific energy at section 2, which will still remain at the critical depth, EC plus delta Z. So E1 dash we can write it as Y dash plus V square upon 2G. EC we know, and delta Z we have to find out. So y dash, it is given in the question that y, it is to be raised to 2.4 meter. So y dash is 2.4 plus v, this we have to find corresponding to this new depth. So we know the total discharge, that is 26.735, as we saw earlier. Total discharge is this much. So discharge divided by area. Area is 2.4, this is the new depth, into width is 3.5 meter. Q square divided by 2 into 9.81, and EC is equal to, EC was 2.718 meters, 2.718 plus delta Z, and if we solve this, delta Z comes out to be 0.2 meter. So from here we can see this delta Z is more than the delta Z max, because we are causing a flux in the upstream condition. So it was flowing something like this, but and this depth was 2 meter, but we wanted to change this depth to 2.4 meter. So if we want to change this depth, then this hump will be greater than delta Z max, and this will still be at pi c. Let's move on to the next question. This is a rectangular channel is 3 meter wide and carries a discharge of 15 cubic at depth of 2 meter. At a certain section of the channel, if it is proposed to reduce the width to 2 meter and alter the elevation by z amount to obtain critical flow at contracted section without altering the upstream depth. So here both the things are happening. Here it is something like this. In the plan there is a reduction in the channel width, and in the elevation there is a hump also. So these two things are such that the contracted section is, what it is saying is, to obtain critical flow at the contracted section. So at this section it should be critical flow. And so the equation which we know for the hump case is E1 is equal to E2 plus delta Z. But here this E2 will be corresponding to the critical condition, because this is asking for the contracted section should be at critical condition. So it will be E1 is equal to EC plus delta Z. So first of all, let's find out the E1 and EC. So this is the channel, 3 meter wide and depth is 2 meter. Q is given, which is 15 cubic. And so V is equal to 15 by 6 is 2.5 meter per second. And from here specific energy at section 1, here specific energy write as Vy plus V square upon 2G is equal to 2 plus V is 2.5 square upon 2 into 1.81. It is equal to 2.319 meter. Now we are bringing it is saying that after a certain section it is proposed to reduce the width to 2 meter. So this width here is 2 meter. So let's find out the critical depth of flow corresponding to this contracted section. So discharge per unit width will be equal to 15 by 2 is 7.5 meter cube per second per meter, and we know the critical depth is equal to q square upon g to the power 1 by 3. From here 7.5 square upon 9.81 to the power 1 by 3, which is coming out to be 1.789 meters. And from here EC we won't need. So the equation which we were following is E1 is equal to EC plus delta Z, because by this hump and plus the width contraction, this energy is coming at critical specific energy. So this we can write as YC plus Q square upon B square YC square upon 2G plus delta Z. So we know all these values. The thing to notice here is we will calculate this critical depth at corresponding to section 2, because the critical depth corresponding to section 2 will be something different, because the discharge per unit width is changing. And so if we put the value here, whatever we found out is 1.789 plus q is 15 square divided by 2 square into 1.789 square 0.81 plus delta Z, and this E1 was equal to 2.319. From here delta Z is equal to minus 0.366 meter. So it is coming out to be negative, which means the channel bed should be lowered rather than increasing. It should be, the height should be decreased, so we can create the critical flow condition at section 2. Now similarly, the next question is a rectangular channel 5 meter wide is 5 meter and depth of flow is 3 meter. Bed slope is given. We have to find out the minimum width of throat and maximum height of hump to produce critical depth without changing the water level. So there are two cases. First we have to find out the minimum width, and second is the maximum height of hump. So let's do it one by one. Again here we have to find out the velocity using Manning's formula till 1 by n r to the power 2 by 3 s to the power 1 by 2. R is equal to a by p, which is equal to 5 into 3 divided by 3 plus 3 plus 5, and so this is 15 by 11, 1.363 meter, and the velocity from here 0 to the power 2 by 3 and 1 upon 1200 to the power 1 by 2. So V is equal to 1.774 meter per second. Q is equal to velocity into area. Area is 15. Q is 26.615 meter cube per second. So in the width contraction case, we know that the specific energy between the two sections does not change. Whatever the specific energy is at section 1 will be the same at section 2, and it is saying that the maximum contraction we have to find. So for maximum contraction we know that the section 2 will be at critical depth. In the elevation if we see, it will be at critical depth, and we know the specific energy E1 is equal to E2, but E2 will be equal to EC. So first of all let's find out E1 is equal to y plus v square upon 2g, and which is depth of flow is 3 meter here, plus velocity was 1.774 square divided by 3 into 9.81. This is coming out to be 3.160 meter, and we know that this will be equal to EC. EC is equal to 3 upon 2 YC. So critical depth of flow at section 2, YC is equal to 2 by 3 into EC is equal to 2 by 3 into 3.160. From here YC is equal to 2.107 meters. And now we have to find out the widths corresponding to this depth of flow. But again at section 2 it is a critical flow condition. So for critical flow we know that Q square T upon G A cube is equal to 1. And from here Q square T is B minimum divided by G into B minimum cube into YC cube is equal to 1. And now we will just put the values here. Q is 26.615 square into B minimum 9.81 into, if we just cut it out, B minimum square into YC cube. YC was 2.107 cube is equal to 1. From here B minimum is equal to 2.778 meters. That's it. And the second part is maximum height of hump. And so the maximum height of hump will again be such that it is critical flow condition here. This depth will be yc, this depth is something y1, and so here energy is E1 and here energy will be E2, and this is delta Z max. So from the energy equation we can write it as E1 is equal to E2 plus delta Z max, and for the maximum height of arm E2 is equal to EC. So for EC, first of all, YC is equal to Q square upon G to the power 1 by 3, and Q, capital Q, we know 26.615 divided by width of the channel is 5 meter. Here it was 5 meter, square divided by 9.81 to the power 1 by 3. This comes out to 1.424 meters. And so the EC is equal to 3 by 2 YC, 3 by 2 into 1.424, which is equal to 2.136 meter. For E1 we calculated earlier, this was 3.160 meter. So putting it in the equation, it is 3.160 is equal to 2.136 plus delta Z max. So delta Z max is coming out to be 1.024 meter. That's it. I hope you understood it. If there is any doubt, you can ask me.